Honorable Chairman, dear listeners, my name is Miha, and I have been invited to tell you about the characteristic times of ionization, charge exchange, and ion confinement in an ECR ion source, or plasma characteristic times for short. I will be describing a new method for the experimental determination developed in a collaboration between LPSC, UFIL, GANIL, and STFC, and some of the results obtained through it. A brief advertisement before I start. If something I say during this talk doesn't make sense, then hopefully this article introducing the method helps clarify things. So go ahead and check it out. So, what characteristic times? The characteristic times are defined by the so-called balance equation. In the context of ECR ion sources, the balance equation is, in my opinion, the mother of all equations. It defines a coupled group of differential equations describing the temporal evolution of ion population densities in the ion source plasma. The model described by the balance equation consists of stepwise ionization via electron-ion collisions, charge exchange between ions and neutral atoms, and losses from confinement. The rate at which ionization produces higher charge state ions depends on the electron density and the ionization rate coefficient, which itself depends on the electron energy distribution, or EED. The characteristic time of ionization can be identified as the inverse of the ionization rate. Charge exchange is thought to occur mainly between the neutral atoms and ions rather than between two ions, as the repelling Coulomb force and the increasing ionization potential of highly charged ions causes the charge exchange cross-section between ions to diminish rapidly. The characteristic time of charge exchange then is determined by the neutral density and the rate coefficient of charge exchange between neutral atoms and the ion in question. Finally, the confinement time is defined by the loss term in the balance equation for a given ion population. The loss term is the one which determines the rate at which ions escape confinement from the plasma and become available for beam formation. In short, the balance equation tells us how quickly or slowly are different ion populations built up in the plasma, and it determines the final shape of the CSD in plasma, the charge state distribution. Consequently, it determines, along with the extraction geometry, how much of the desired type of ion will the ion source operator see in the beam. The experimental determination of the characteristic times at play in the balance equation then is vital for the continued development of ECR ion sources. So, in order to measure the characteristic times, we need to probe some phenomenon where they are involved. In effect, this would mean measuring the ion population densities. Measurements of population densities must be made indirectly to avoid perturbing the state of the plasma, which would corrupt the measurements. We thus resort to determining the densities from the transient time series of the extracted ion beam currents. We have used this equation to correlate the extracted beam current to the ion density inside the plasma, and to recast the balance equation in terms of the beam currents. So combine this equation with the balance equation, and you are left with this neat equation for the extraction beam currents with the convenient definitions of A, B, and C. The fitting parameters A, B, and C can be obtained by first measuring the beam current transients of all the available charge states, then taking the currents of charge states Q-1 and Q+1 as input values, we solve the current balance equation for the signal of the charge state Q numerically as a function of time, for example, using the fourth order Runge-Kutta method. The correct values of A, B, and C minimize the residual between the numerical solution, here in calligraphic I, and the actual measured current for charge state Q. Once we have determined the coefficients A, B, and C, we can determine from them the electron density and the average electron energy, which is hidden inside the ionization rate coefficients. Once the electron density and average energy are obtained, we can use those to calculate the characteristic times, again, from the definitions of the fitting parameters A, B, and C. It can be shown by performing some amount of algebraic acrobatics on these definitions of A, B, and C, that this equation in two unknowns, the electron density and average electron energy, remember hidden here in the ionization rate coefficient, applies. Now this equation has an infinitude of solutions consistent with the parameters A, B, and C, a mathematical fact. Luckily, the solution set may be curtailed by physical considerations. For example, we may make the requirement that the characteristic times be positive, as they should be, but also the requirement that the electron density and average energy be within a range which one can realistically expect in an ECRIS. So, let's go over the algorithm for determining the solution set of this equation in two unknowns. We focus on a general charge state Q, which means that we require ABC parameters for Q minus 1 up to Q plus 1, meaning we have to measure at least 5 consecutive transients to obtain those parameters. First and foremost, we define a penalty function to turn the solution of the equation into a minimization problem. We do this by subtracting the right-hand side from the left-hand side of the equation and dividing by the left-hand side. By minimizing the absolute value of this equation, we obtain solutions which satisfy the original equation. We then calculate in advance all the ionization rate coefficients using different average energies of the EED, which, as I mentioned, is... Oh no, I didn't mention it. I'll take the opportunity to mention it. The rate coefficient is calculated by taking the weighted average of the event cross-section over the distribution of the relative speeds of the interacting particles. In order to calculate the rate coefficient, then, one must make an assumption regarding the particle energy distributions. We have presumed the electrons to be much faster than the ions, which is quite reasonable within the context of the ECRIS, where ions may reach average energies on the order of 10 electron volts, while average electron energies can be on the order of a kiloelectron volt. We also assume that the electron energy is Maxwell-Boltzmann distributed, although it is possible to extend the method to consider other distributions as well. One simply needs to recalculate the rate coefficients using the desired distribution. The necessary cross-sections as a function of energy have been experimentally determined, and we take them from the literature. So we can calculate all these ionization rate coefficients. We then create interpolation functions within the calculated range so that we can evaluate the rate coefficient quickly using those interpolation functions. We do this to avoid the computationally heavy integration over the EED. Next, we choose the limits for the solution space based on physical considerations. Here we have chosen the upper limit of the electron density, here on this axis, to be the cutoff density for 14.5 gigahertz microwaves. The lower limit has been conservatively chosen to be 1 × 10⁻11 per cubic centimeter based on 1+ stopping experiments. The average energy of the EED has been constrained from below to 10 electron volts, the order of magnitude of the plasma potential, and from the above to 10 kiloelectron volts based on experimental evidence. Then we choose a dense array of electron densities and begin to iterate over this array. We fix the electron density and minimize the penalty function along this line. Say we find a minimum here demarcated by the red dot. We do this for each electron density in turn to obtain a set of minima. Now, we must also take into account the unfortunate fact that the experimental cross-sections of the experimental ionization cross-sections are somewhat uncertain. The relative uncertainties range from 10% to as much as 200%, but we can take them into account by means of a Monte Carlo approach. We repeat what we did just now, only we add a random bias factor within the uncertainty range to each rate coefficient. We repeat this, so we obtain another set, something like this. Note that we also displace each electron density by a small amount to cover to obtain an even tighter coverage of the solution space. And we repeat this 1,000 times to sufficiently sample the different uncertainty bias configurations to make sure that we have tried all the possible ways that we may have misevaluated the rate coefficients. And finally, we apply the physicality constraints, which require that the characteristic times calculated at the points of this solution space must be positive, which leaves us with a slightly rarefied solution set, which can be further rarefied by demanding the penalty function to be closer and closer to zero. After all, some minima may have rather large numerical values, but we choose to accept penalty function values which are very nearly zero. We actually find that we can set the limit to 10 to the power minus 9, and we still find thousands of valid solutions. Now, it must be noted that our method relies on the assumption that the coefficients A, B, and C remain constant in time during the measurement. In effect, this requires that the neutral and electron densities, the shape of the EED, and the ion confinement conditions do not change. These assumptions are the better the smaller a perturbation we cause on the plasma during our measurement, which brings us to the question of how to produce the current transients in the first place. Here's a picture of our experimental setup. So to produce measurable beam current transients, we first ignite a support plasma in the ion source, pictured here. The support plasma needs to be chosen in such a way that its extracted CSD won't overlap with the transients we wish to measure. Because of this, the easiest support gas to work with is probably helium or hydrogen. But with adequate resolving power, one could theoretically use any support gas. A metallic element, potassium for instance, is then injected into the ion source by means of 1+ injection. A pellet is heated at the 1+ ion source, pictured over here, which causes singly charged ions to be emitted. These ions are then guided into the ECRIS along the 1+ beam line. One uses a variable potential, delta V, between the ion source and the 1+ source to adjust the energy of the 1+ ions as they enter the source to optimize their capture in the plasma. Different ion optical elements are also used to select and guide the ions along the beam line, and to control the emittance of the injected beam. A Faraday cup here can be used to measure the amount of material being supplied to the ion source quite precisely, which makes the 1+ injection method superior to laser ablation or sputtering in the case of this method. Because we are interested in transient behavior, we use an electrostatic chopper to produce a square-shaped injection pulse. The temporal width and intensity of the pulse are kept as small as possible while producing measurable beam currents, simultaneously minimizing any perturbance of the support plasma. The 1+ ions injected into the ion source during this square pulse then become subject to the balance equation, which determines the shape of the transient time series of the extracted beam currents. Once they escape confinement from the source, the ions are extracted and the resultant beam current transients are measured downstream at the N plus Faraday cup over here at the end. The dipole here at the N plus beamline is used to separate the different ion species based on their charge to mass ratio. These very same beam current transients are used to determine the parameters A, B, and C via the numerical method described earlier. And here I have an example of a measurement. Here's the square pulse of the 1 plus injection. So this 5 millisecond pulse goes in, and out come these transient current bumps. And these are measured here at the N plus cup, while the 1 plus command is measured over here at the Faraday cup. And then, as per the results, we've applied this method to two different configurations of the Phoenix type charge breeder ECRIS at LPSC. The configurations are different all the way down to the support gas species. Helium in the former 2020 configuration and hydrogen in the new 2021 configuration. This table tabulates the operating parameters used in the former and the new configuration. The magnetic field configurations too were different, and a slightly higher microwave power input was used in the new configuration. In the new configuration, a smaller intensity of the 1 plus injection pulse was used. Now these figures show an example of the solution sets obtained for potassium 10 plus in the two configurations. You can see that we can find solutions which are consistent with the fitting coefficients in a broad range of electron densities and average energies of the EED. The heat maps show where the greatest concentration of solutions can be found, and the histograms on the figure margins show the distribution of electron densities and average energies in the solution sets. Note that the heat maps are normalized such that an integral over their area equals 1. Similar solution sets were obtained for potassium charge states 5 plus through 10 plus. The table below tabulates the most probable values of electron density and average energy obtained from the maxima of these histograms. From the table, we can infer an increase in the electron density from the former to the new configuration, in particular in the case of the high charge states. A similar increase is seen in the case of the average energy of the EED. Especially in the case of the average energy, we can see a trend of increase in energy as we move towards high charge states downwards in the table. And especially in the case of the new configuration, we can also see that the electron density is higher for the higher charge states. This is consistent with the so-called nested layer model, where the low charge states ions originate from the periphery of the plasma, and higher charge states from smaller radii around the central axis of the plasma chamber, with the highest charge states originating from the plasma core. The nested layer model is supported by both simulations and experiments, and in case I wasn't able to perfectly explain it, ask about it because I've got a bonus slide about the nested layer structure. It's interesting to note that although this method is at its heart based on a zero-dimensional model, which basically treats the plasma as a point-like entity, we obtain results which imply spatial variations in the support plasma properties. This is because we make the fits to only 3 charge states transients at a time, and within the context of the nested layer model, where the different charge states originate from different plasma regions, this means that we obtain results corresponding to those regions. Finally, we plot the characteristic times of charge exchange, ionization, and ion confinement, which have been calculated in each point within the solution sets. Because the solution set encompasses a wide range of possible electron densities and average energies, we also obtain a distribution for the characteristic times. This is why the uncertainty bounds drawn on the figures here are not to be interpreted as traditional uncertainty bounds arising from the measurement. The uncertainty bounds are defined such that they enclose 34.1% of all characteristic time values above and below the median value, which is represented by the data point. If we were able to impose stricter constraints on the electron density and average energy, we would obtain smaller uncertainty bounds. Hence, the following interpretations have been made based on the median values. Some decrease can be seen in each of the characteristic times. In the case of the charge exchange time, this can be attributed primarily to the change in the support gas species, charge exchange time in subfigure A. In the new configuration, we used molecular hydrogen, which has a larger diameter and smaller ionization potential than helium. This makes the charge exchange cross-section of molecular hydrogen larger, easier to hit, than that of helium, and correspondingly decreases the charge exchange time. Easy to hit, takes a shorter time to hit it. There also exists in the charge exchange time a minimum around potassium 8+, which is attributable to the nested layer structure. Knowing that the charge exchange cross-section increases with the ion charge state, if the neutral density were uniform, we would expect a constant decrease in the charge exchange time. The fact that we see an increase towards the high charge states indicates that the neutral density is decreasing. In the ionization time, subfigure B, we observe a small decrease in the ionization time for the low charge states and a somewhat larger one for the high charge states. This is consistent with the increased microwave power input and the increase in the average electron energy we inferred from the solution sets. An important acid test for the method is that we find that the distinct jump in the ionization time between 8+ and 9+ here, which is consistent with the electron shell closure for potassium 9+, i.e. potassium 9+ is much more difficult to ionize further, as we should expect. The ion confinement time, subfigure C, has decreased for the high charge states, which allows the ions, once produced, to quickly escape and become available for beam formation. It's noteworthy that in particular in the former configuration, the ion confinement time is non-linear. A linear fit to the data would yield negative confinement times for the low charge states. A power law fits the data much better, which is an important find as the assumption of a linear dependence is often made. Note also that the confinement time is found to be on the order of 10 milliseconds for the high charge states, roughly an order of magnitude higher than what is conventionally reported. Such a long confinement time could allow ions to be heated to temperatures of 5 to 28 electron volts, which are reported based on Doppler broadening of the ion optical emissions. The low charge states have shorter confinement times, and it can be shown that while the low charges may be magnetically confined, the collisionality of the high charges interferes with their magnetic confinement. This suggests that the confinement model of the high charge states is different from that of the low charge states, and the electrostatic dip confinement in particular is consistent with the aforementioned high ion temperatures. Finally, the characteristic times can be used to explain the change in the charge breeding efficiency, which has been overlaid over each plot in magenta. The decreased charge exchange time depletes the high charge states, supplying the lower charge states populations, while the decreased confinement time allows, in particular, the potassium 9+ to escape confinement more easily in the new configuration, as you can see. Meanwhile, the shell closure of potassium 9+ works to inhibit ionization from that charge state, causing the peak in the efficiency to occur around potassium 9+. It can be concluded that the optimization of the charge breeding efficiency of any given charge state requires the decrease of charge exchange time for the charge states above and the decrease of ionization time for charge states below and a decrease of confinement time for that specific charge state. Furthermore, the optimization will be easiest for a charge state corresponding to a closure of the electronic shell. Now, I hope this talk has been of interest to you all, and if you have any questions, I'll be happy to try and answer them. Thank you very much for your attention.